Big omega notation captures lower bound of algorithm, whereas big O captures the upper bound. So in big O notation, what we were trying to say was we wanted f of x to be less than or equal to c times g of x. In big omega notation, we are going to have exactly opposite. The easiest way to define big omega is a function f of x is big omega of g of x if and only if g of x is big O of f of x. We use omega notation, big omega notation for lower bounds. So for example, if I wanted to find a maximum in a list of n elements, then we would need at least n amount of work if we could compare only 2 elements at a time. An algorithm whose running time is big omega of n square is inefficient compared to an algorithm whose running time is big O of n log n, because in this case we are basically saying the complexity of this is bounded from above by n log n, and the complexity of this algorithm is bounded from below by n square. That means the complexity is strictly more than n square or equal to n square, whereas here in the other algorithm it is less than or equal to n log n. We can combine big O and big omega notation with big theta. So we say that f of x is big theta of g of x if and only if we can find c1 and c2 such that the function f is bounded from below by c1 times g of x and bounded above from c2 times g of x for any value of k. So we can observe that f of x is big theta of g of x if and only if it's both big O and big omega of g of x. So one example we have here is x plus 1 square is big theta of 3x squared. Here is a quick recap of big O, big omega, and big theta. So big O says that fx does not grow faster than g of x. Big omega says it grows at least as fast as g, and big theta says that they grow at the same rate. Now there is an easy way to find big O, big omega, and big theta. What we can do is we can take the ratio of fx to gx and we can see how this ratio behaves as x tends to infinity. If this ratio is 0, that means we have fx is big O of gx, and I would ask you to review each of this, and we will do some examples associated with this in class. Here is some terminology that we used for different kinds of algorithms. So order 1 is what we call a constant complexity. Big theta of 1 is what we call constant complexity. Theta of log n is what we call logarithmic complexity. We have linear arithmetic complexity, which is n log n, polynomial, exponential, and so on. The reason we care about complexity is because we can use this table to see how the time taken by an algorithm varies as we look at different problem sizes. So let's imagine we have algorithms that are complexity log n log n square, 2 to the power n factorial. And let's try to see how the algorithm will behave for different values of n. What we can observe is if the complexity is log n, then the time that it changed is from 10 to the minus 11 to 10 to the power minus 10. Roughly, we are in the same ballpark. Here, there is a substantial change from 10 to the power minus 10 to 10 to the power minus 5. Here, the change is somewhat similar. N square, the change is getting even worse from 10 to the power minus 19 to almost a minute, at least several seconds. With 2 to the power n, we can observe things get really bad really fast. So when the problem size is just 10, it was 10 to the power minus 8 seconds. We are talking about sub microsecond. But for 100, the answer went from below microseconds to several thousand, several million years. And that's why exponential complexity can be a significant bottleneck for algorithms. Now, that said, I want you to be aware that there are people who have tried to identify optimizations so that you don't run into this kind of behavior all the time. So what it allows you to do is basically develop algorithms where worst case complexity, yes, is really bad, but on average case, it finds the answer much more quickly. Here is another way to look at the same data. What we want to see here is how functions grow at different rate. So 2 to the power n is growing quite a bit faster. N square comparatively is growing not as fast. N is even slower, and so on and so forth. Important thing to remember here is this is not a linear scale. You're going here from 1 to 4, 8, 16, etc. Once again, we have reached the check before you go ahead slide. Here are a few things I want you to do before you do the review quiz. One is plot a few functions like n squared 2 to the power n to see the growth of exponential functions. Exponential functions are one of those functions that appear very mild at the beginning but grow very, very fast as the value of x or the value of n in this case increases. Even for exponential functions, look at graphs of something like 1.1 to the power n, 1.2 to the power n, etc. You will see some interesting results, and I will talk about it in class as well. I want you to make sure you review the slide with the heading using limit to express big O, big omega, big theta. That slide is going to be very handy to figure out big O, big omega, or big theta of different functions. We have reached the end of the module, so do the review quiz at this point. And if there are questions, make sure you discuss it with me or the TA.